Let's go over theoretical probability versus experimental probability. So let's say we roll a die. On the die we're going to have a side that's a 1, a side that's a 2, a side that's a 3. Let's make these a little bit bigger. A side that has 4 dots, a side with 5 dots, and a side with 6 dots. So there are 6 sides and 6 different outcomes. So if we want to see the probability of rolling an even number, just take a look. We see that we have 1, 2, 3 even numbers out of a possible 6. So probability of getting an even number is 1 out of 2. And this is theoretical. The probability of rolling a 1 is, well, there's only one side that has a 1 out of 6 total outcomes, so 1 out of 6. Probability of rolling a 2, okay, there's only one 2, so it's again 1 out of 6. Probability of getting a prime number. So what are the primes? 2, 3, and 5. So it's going to be 3 out of 6, which again is 1/2. So this is theoretical. We assume that if we roll a die, any side has as equal an outcome or equal chance of coming out. So it's just the number of favorable outcomes, the number that we want, out of the number of total outcomes. So if we want there to be an even number, there were 3 even numbers, and we'll say that they're just as likely to come out as any other numbers. So it's 3 out of the total 6. Okay, this is different than experimental probability, because experimental probability is based on an experiment and data. So if we roll a die, theoretically, since it will have an equal opportunity of coming out, any of these outcomes, we should get the same frequency. So if we roll a die 60 times, we'd expect it to be spread out. We get a 1 10 times, a 2 10 times, 3 10 times, a 4 10 times, a 5 10 times, and a 6 10 times. Okay, that's theoretical. Since they all have the same likelihood of occurring, we expect it to be evenly distributed. Okay, but that's not always the case. So, for whatever reason, when the die was rolled 60 times, a 1, instead of coming out 10 times, came out 15 times. A 2, 8 times. A 3, 7 times. A 4, 20 times. A 5 only twice. And a 6, 8 times. So this should add up to a 60. Let's just check it quickly. 15 plus 8 plus 7 plus 20 plus 2 plus 8. So that is 60 times. So things didn't go as planned. For whatever reason, the 4 came out a lot more than the other numbers, and then a 1 came out 15 times. It wasn't the evenly distributed 10 times. So experimental probability will be based on these outcomes. So based on our experiment where we rolled the die 60 times, it seems like you're more likely to roll a 4 than you are to roll a 5, which only came out twice. So here, if we want to find a probability of rolling a 1, well, we'd say out of every 60 times you roll it, we'd expect to get it 15 times. So 1 out of 4 times. It's a lot different than the 1 out of 6 times we had before. The probability of getting a 2, we saw a 2 came out 8 times, 8 out of 60. This can be reduced. 4 goes into both of these, so 2 out of 15 times. Okay, that's a lot less likely than the 1 out of 6 times that we had before. And just for example, the probability of getting a 4 would be 20 out of 60, or 1/3 of the time. we want to find the experimental probability of rolling an even number. Okay, these are the even numbers here. Let's see how many times they came out. So that's going to be 8 plus 20 is 28, plus another 8 is 36. So 36 out of the 60 times. Let's reduce that. 6 goes into both, 6 over 10. 2 goes into both, 3/5 of the time. So for theoretical probability, we base it on everything being as likely to occur, or based on the size or whatever it appears it would be. Experimental probability is based on data from actually doing the experiment and seeing how many times it does come out. So make sure when you do experimental probability, you base it on the frequency that it occurred out of the total times that it was tried.